Good evening. Welcome to the second in our new quarterly series of public lectures on what we call the frontier of cosmology. So the idea of the Frontiers of Cosmology series is to every quarter bring in a researcher from the front lines of frontier experimental research in the fields of cosmology, particle astrophysics, and gravitational waves. We held the first of these events in the spring quarter of last year. This is the second. And based on the really enthusiastic turnout tonight, I think this will definitely give us the motivation to continue doing these each quarter. So I'd like to welcome you to the event and to first introduce Dean Peter Atkinson, the Dean of UCR's College of Natural Arts and Sciences. Welcome, Peter.
Right, thanks for the introduction. It's a real privilege and honor to be at another physics event. Welcome to our campus. Welcome to our speaker from UC San Diego. I have to, give a sincere congratulations to the department for everyone for coming out tonight, because this is one dynamic department. And is Michaela in the audience from the event last Tuesday, which was the dark matter night? Is she there? No? Okay, well, okay, well, congratulations on a wonderful night. I know we're talking about tonight, but Shan Wen asked me to go to the dark matter night down in the department. I think it was last Tuesday night after the new faculty celebration, and I wish I could have stayed all night, but my wife wanted me home, and I was already way too late. But it was such a fantastic event because I saw how well you managed it and how every student there was asking questions about the material that was being presented. And I was learning so much, and it's a testimony to you, to the students, the level of trust you have in the department where anybody can ask questions. And that was a job really well done. So I'm glad I've got this opportunity to thank you and really appreciate you and the students and everybody who organized that for a job well done. This is just another example. It's a little more formal, where we have a speaker from a sister campus talking about these subjects which are of intense interest to all of us. And thanks for coming. Congratulations again to this extremely dynamic Department of Physics and Astronomy that really does the college and UCR proud by having events like this constantly, always striving to do more for your department and for the campus. And with that, I'll introduce the mastermind behind the whole thing, which is the chair of your department, Shan Wen Tsai.
Okay, welcome everyone to, on behalf of Physics and Astronomy Department to this event. I would like to start, before we get to that, I would like to give you some updates about the department. We have a number of exciting news that include our recently created astronomy track for our undergraduate physics major, a new course that has been created called Techniques of Observational Astronomy, where our students get to go to the Goat Mountains Astronomical Reserve north of Joshua Tree to make observations using a telescope there. We have a new PhD track in astronomy, a separate track, and also a partnership with the University of Hawaii for a student exchange program that is funded by the National Science Foundation. We also have a new multi-institution center called MURI QVET, which is pushing a new field of research called quantum vibronics. That is something that is exploited for new properties of materials, and has applications in energy and also live matter, including photosynthesis. Among the many other exciting news, definitely what we're celebrating today, which is the Frontiers of Cosmology series that we are here for, is brought to you by our Center for Experimental Cosmology and Instrumentation. That's a brand new center that's being formed. It's a new effort for studying cosmology with a focus on designing experiments and building instrumentation for the most sensitive of cosmological measurements, with instruments being built right here on campus. And that will then be part of large international collaborations all over the country and all over the world. Aside from the research that this enables, this opens new opportunities for our students to do amazing research. And the focus on instrumentation gives training opportunities for them to perhaps go on and lead on scientific research, but also to acquire training for high-skilled jobs, including jobs here in this area. The current core of this center is composed of Nobel laureate Barry Barish. He won the Nobel Prize in Physics in 2017 and also received the National Medal of Science last year from the United States President. And it's composed also of 3 junior faculty. Jonathan Richardson, who is hosting the event today, Sean Westerdale, and Steve Choi. The center also brings together the various strands in the department, including astronomy, atomic, molecular, and optical physics, physics of quantum materials and devices that will enable the precision measurements, nuclear and astroparticle physics. As part of this major effort, we are embarking in a fundraising effort. So to help us, that will allow us to do a few things. It will provide scholarship for undergraduate and graduate students to do research in these forefront areas. It would enable purchase of specialized and shared pieces of equipment, and also, more importantly, for more outreach activities, such as this one, where we can share the work we do with the broader community on campus, such as this event, but also in the community, where we go to local schools and libraries and science fairs. Just this past Sunday, we had the 30 Cub Scouts coming in the physics building to do various physics activities. So that's one such example. So if you would like to learn more about the center and learn how to give, we have a QR code it's in the pamphlet, in the program here today. And also, as you walk out, it will be in the posters. If you'd like to engage and discuss more ways to participate in this enterprise together with us, please reach out so we can discuss more. And finally, now to introduce our distinguished speaker for today, I am going to present to you Professor Steve Choi to do that. He is our most recent faculty to join the Center for Experimental Cosmology and Instrumentation. Okay, Steve.
Thanks everybody for coming. Are people outside still? Can people come in more because there's space you can squeeze into? Yeah, please all come in now. Come in now so that you can catch the talk. Yeah, so I have the privilege to introduce our distinguished lecturer tonight, Professor Brian Keating from UC San Diego, where he's a Chancellor's Distinguished Professor of Physics. Brian received his PhD from Brown University, then was a postdoctoral fellow at Stanford and Caltech before joining the faculty at UC San Diego. He's the principal investigator of the Simons Observatory. This is the flagship cosmology experiment of this current generation, as you'll hear more about soon. He's won a number of awards, and we would need a long, long time to get through all of his illustrious career. So if you'd allow me, I just picked 3 quick things to say. First, he's one of the leading pop scientists today. I hope after this talk, you'll get a chance to pick up one of his best-selling books and get it signed. And if you haven't yet, I encourage you to check out his YouTube channel, podcasts, Into the Impossible. Second is that he's a commercial pilot and was inducted into the International Aviation Hall of Fame in 2022. And in fact, he actually flew himself over here from San Diego to Riverside Airport, which is very cool. And lastly, and personally, Brian is the one who got me started off on my own journey in cosmology. About 14 years ago, he took a chance, he gave a chance to this average undergrad student at UC San Diego with no relevant experience or skills whatsoever. Yet he accepted me into his lab, so that's how it all began. And so, Brian, I wanted to thank you for the opportunity you've given me. Thanks to you, I have this job today, doing what I've always dreamed of. And I feel honored to be able to introduce you tonight as a collaborator of yours. So please join me in welcoming Professor Brian Keating.
Wow. Wow. That is, I'm verklempt. Anyone know what verklempt means? Overcome with emotion. See how great an altitude up in the highlands that Steve has achieved. And don't listen to him. He came in with many skills, many relevant skills. And he was, probably wouldn't like me saying, but he's probably voted most popular man on campus more times than I can count. He's a gem. You guys are so lucky to have him. Thank you, Dean Atkinson. Thank you, John. Thank you, Xingwen. We've known each other for so long, and now I'm going to try to do the most difficult thing, which is to share a screen on Zoom. Don't we all love Zoom? You guys are waiting so patiently to see a Zoom lecture. No, it won't be a Zoom lecture like we had. Uh-oh, someone else is sharing. Gotta click stop share here. I'm going to figure it out. I'm going to experiment with it. So many people here tonight. It reminds me of yesterday on campus, lines to vote. Who waited online yesterday to vote and waited hours and hours? I sure did. And I'm sure glad that the election is over. God, that was an event. But I always say people love cosmology and they love astronomy because there's no such thing as a Republican constellation or a Democratic asteroid. It's a safe space. It is truly one of the few safe spaces that we have. And we need those spaces for the mind to grow and to really do what we humans do uniquely so. And I'm going to walk you through a little bit about what we do as cosmologists. So it's an honor to be here. It's my 4th or 5th trip up here. Campus gets bigger and better every time I come to visit. Kind of jealous, your proximity to Big Bear. The title of tonight's talk is specifically, was there a Big Bang? Not was there a Big Bang. Was there a Big Bang? And the notion of what the Big Bang is the most dominant paradigm, perhaps in all of science, as I'll make a case for just as we proceed. But it is not at all clear that the Big Bang happened, nor is it clear that there was only one Big Bang, and nor is it clear that there's only one universe. And these are the most stunning, most mesmerizing questions that I could possibly think to answer. So it's so gratifying to see so many people interested on a, Wednesday night? I lost track of time the last couple of days. But on a Wednesday night to come out and hear about the origin of the universe. And as Steve mentioned, he's one of the key players on this flagship project called the Simons Observatory, which is a roughly $200 million project built from scratch in the Atacama Desert of northern Chile. It's at an altitude of 17,200 feet. Steve and I have been there many times. It's like a version of Mars that you can go to, visit, and in fact, NASA trains some of the astronauts that eventually will go to Mars in this very Atacama Desert location. It's extremely foreboding. It's very difficult to get to. It's very dangerous, in fact, to get there. And we had to build this observatory from scratch, from bare rock and dirt. We are self-sufficient, and we've recently begun commissioning observations, and I'll talk a little bit more about that. Oh, and these pointy looking things in the background, that's not like Big Bear. Those are active volcanoes. So on occasion, we'll get a weather forecast, and the weather forecast will include 30% chance of volcanic eruption. So something we don't really have to deal with in Southern California, but it makes it all the more interesting. So we're going to do a cosmology crash course tonight. For those of you who don't know about cosmology, that's fine. For those of you that do, I hope to provoke maybe an emotional reaction to some of the things I'm going to talk about tonight, because cosmology, unique amongst all the sciences, unifies all branches of human endeavor, including those that make us uniquely human. The word human comes, we are called humans, our species is Homo sapien. Homo means man, woman, and sapien means wise or knowledge. And the question that we can uniquely ask amongst species is, where did we come from? How did it all begin? And where, if anywhere, is it all going? And these impact everything from physics to philosophy, even to theology. And we'll discuss all of those tonight. As I said, it may be emotional, it may be controversial. That's what makes it so much fun to be a scientist. I'm only disappointed, and only because of Steve's graciousness, that I remained here when I found out that Barry, my hero, my mentor, is not here tonight, unfortunately, but I have interviewed him more times than I can count, and he did me the gracious gift of writing the foreword to my second book. So I hope to, I thought there'd be 35 of you tonight, so I bought like 35 books. So if you can't get a book, I will send you, especially, oops. So now oh, it's gonna go to my YouTube channel, cool. All right, there we go, back up here. So unlike your other professors here, me and old, Professor Steve Choi, I let you use your cell phone tonight to take pictures of QR codes. And I don't ask you for money either, but you should consider donating if you have the capacity. So Barry's a hero of mine. He really has influenced my life in many ways, not just because he won the Nobel Prize, but because of his humility, his humanity. And he shared with me something that really became the reason that I wrote the second book of 9 interviews with 9 Nobel laureates, including Barry. And that was a vignette that he told me upon winning the Nobel Prize, apparently. I may never know this, given that my first book is called Losing the Nobel Prize, not winning it. But Barry told me, when you win a Nobel Prize, you go to Stockholm, you eat some reindeer, and then you dress up and you meet with the King of Sweden. And then you bow down and he puts a golden medal around your neck, and you get a check for, in Barry's case, $250,000. And they want to make sure you're not going to come back and ask for their money back. Oh, I didn't get it. I left it in my suitcase. No. You sign a ledger. It says, I, Barry Barish, received my prize. So you won't come back, as people have come back in the past. And he said when he saw that book, he opened it up and he saw who won it a year before, 2 years before, 10 years before. He saw famous luminaries, Marie Curie, Richard Feynman, and he saw Albert Einstein. And he said, my heart stopped. What do I have, this boy from Omaha, what do I have in common with Albert Einstein, the greatest intellect who ever lived? I am not worthy. And I said, Barry, you're suffering from a condition called the imposter syndrome. It's very common, even common amongst Nobel Prize winners. He said, really? I told him, yes. In fact, your hero, Albert Einstein, felt he was unworthy of being considered the greatest scientist compared to his hero, Isaac Newton. And I said, but wait, Barry, there's more. Because Isaac Newton, too, felt that he was unworthy of being even considered as a great luminary in comparison to his hero, Jesus Christ. Not a physicist, but an exceptional mind. So I said, Barry, this goes back a long time, and you're not the first to suffer from it. So that was part of the inspiration for writing this book, which is really a self-help guide for physicists, for scientists, for engineers. And I hope you'll enjoy it, you'll read it. And I promise you that if you join this mailing list, this QR code, I will send you each a real, genuine sample of the 4 billion-year-old primordial solar system, a meteorite, a real meteorite, along with information about how you can collect them yourself. So please do that. Anyone who buys a book tonight will get one, and then if you join my mailing list, I'll mail you one eventually. So what is tonight about? Well, it's not about cosmetology. Sorry to disappoint. I know the hair and the nails. No, I don't do my nails. My daughters tried to get my nails done the other day. I would not accommodate them. Why does cosmology have this relationship between cosmology and cosmetology? At least it's not being mistaken for astrology. I get that a lot too. Oh, you're an astronomer. I'm a Virgo. Well, who cares, you know? When I was dating my wife 20 years ago, or 18 years ago, she wanted to go see an astrologer to find out if we had a good mixed compatible chakra. I don't know. I know nothing about astrology. But we went to the astrologer and she said, what's your sign? And I said, I think I'm a Gemini. And she gave me my whole horoscope. Then at the end, she said, anything else? And I said, I just want to confirm, I'm born in September. Is that Gemini? Oh, no, you're a Virgo. But the same things are going to happen to you anyway. So astrology is not a science. And that's very important for what we're going to talk about tonight. Actually, cosmetology is more of a science than is astrology. But, and this is important, it shares this prefix, cosmo. Cosmo means beautiful, as in the beautiful appearance that the night sky presents to us. So it's very evocative, but we won't be talking about makeup tips. But I like to think about what we get paid to do as humble employees of the state of California, is we get to address the most incredible, most important questions. The questions that many of you don't know that you have the privilege right now to think about. And that in the later years, you're going to accumulate dogs and spouses and partners and all sorts of things. And you won't have time to think about this stuff. Trust me. Taxes, teaching loads, committee meetings. Am I right, professors? Right? But now you can think about it. I implore you, indulge yourself of these questions. Don't let tonight be the end. Let it be the beginning of this journey in which we, this fragile 3-pound supercomputer on our shoulders, can contemplate everything from the origin of matter to the origin of life, to the origin of consciousness, to the origin of the universe. And we are unique, not just because we're so brilliant we're out of UC school, but because we are human beings, Homo sapiens. We are wise. I told you there is a connection between cosmology and every other science, and that's depicted no more beautifully than here in Wikipedia, the source of all scientific knowledge. If you go to the science page of Wikipedia, it alternates, but currently, or when I took this screenshot, the avatar of science as a whole was cosmology. It was a depiction of the origin of the universe, how it evolved, and where it may be going, and something about the history. That shows you, at least at a popular level, how central, how critical cosmology is to the endeavor of being a scientist. Now, we do cosmology. It's even harder than astronomy. Let me give you an example or an explanation of why I say this. It's impossible for an astronomer to do an experiment. I cannot go to the sun and change its temperature and say, oh, what happens to the sunspots there on the sun or some galaxy? I can't go and do a controlled experiment. It's impossible. But cosmology is even harder because for stars, there's over 100 billion stars in our galaxy alone. So there's many, many samples, many statistical inferences that we can draw from the multiplicity of objects in that field. But you may have noticed, at least for a while, cosmology is concerned with the evolution of the universe. Uni meaning one. Now, I will talk to you tonight about versions of cosmology that have multiple universes. But the sense of the universe being unique is still preserved and maintained. So I like to think of what we do as astronomers and cosmologists like paleontologists studying artifacts from long ago. Like this little creature here, it looks so cute and cuddly. I'd like to get one of those. Some kind of half mammal, half dinosaur. I don't know. I'm not a biologist or a paleontologist. But we're dealing with fossils. In our case, we deal with the oldest light in the universe. Oldest fossil relic that could ever be seen by eyes or telescopes. And so we get to go back in time. That's our benefit. We have a time machine, as depicted here. Your eyes are telescopes. You have 2 refracting telescopes, born standard issue equipment, and they're pretty damn special. They can detect even single photons. They have hundreds plus 180-degree field of view. They can focus and accommodate in ways that a camera cannot, but they have limitations too. But the best part about a telescope is it takes you back in time by looking back in space. Light travels 1 foot in a nanosecond. That means if you're a foot away from me, I'm seeing you in an earlier state, 1 nanosecond earlier, younger. So nowadays, when I say that, older people start to move to the back, but no, you can't get younger necessarily. You're still the same age, but you'll appear in a younger state. Now, to illustrate this, I'll go back to our solar system. The Earth-Sun distance, as many of you know, most of you know, is about 8 light minutes. And imagine this creature called a mayfly, again, from the source of all knowledge, Wikipedia. Look at what the mayfly is comprised of. The primary function of the adult is reproduction. Now, we all know people like that in our daily lives, right? That's all they're concerned with. The mouth parts are vestigial. That means they're legacy products. They don't really serve a purpose. This is not a creature designed for a very long life. And in fact, the average lifetime is about 8 minutes. Now, the moon is about 1.5 light seconds away from Earth. And the sun is 8 light minutes away from Earth. So imagine 2 twin mayflies, born exactly at the same time. I don't know how this was done. One is born near the sun, not on the sun, but near the sun. One is born on the moon, not so close much closer to the Earth. And you see them, and then all of a sudden you see eventually the mayfly on the moon is dead. What do you know for sure about his twin brother on the sun? He's been dead a long time, much, much longer. He's also dead. And so the question is, when you look back in space, you're looking back in time. So how far back can you look? Well, here's an early image from, this is now about 30 years old. This is from the Hubble Space Telescope. It's called the Hubble Deep Field. And essentially every smudge of light, every pixel that's illuminated here is a galaxy, with about 3 or 4 exceptions that are stars in our Milky Way galaxy. And if you count up how many galaxies are in here, there's 5,000 galaxies in this image alone. I think Bahram Abashir, somewhere maybe he's here, he is responsible for taking this picture. And when you look at these objects, they look kind of very interesting, but you might say, well, this is a pretty big piece of sky, right? And so maybe it's not surprising that there's 5,000 galaxies. No, it's actually a very small part of the sky at very high magnification. In fact, it's smaller than a little tiny period at the end of a sentence held out at the end of your hand. That's how big it is on the sky. Smaller than a little dot, a single pixel on the screen even. And yet it has 5,000 galaxies in it. So we can estimate how many galaxies there are in our observable universe by counting how many times it would take to move your finger over the entire sky. And we have about an hour, right, Steve? So we can do that. No, we're not going to do that because it would take all week, all month maybe. But you get about 100 billion galaxies in our observable universe. This universe is enormous. There's no way around it. There's no other description that fits. In fact, we talk about these things as astronomical. We really should call them cosmological because of the capacity, the vast capaciousness of our universe. How far back can we look? Well, with light, our vision ends at this background of radiation called the cosmic microwave background radiation. And this radiation is the result of a fusion process of the first time an electron and a proton got together and said, hey, we make a good pair, let's make hydrogen. It's the first atoms in the universe about 400,000 years after the Big Bang. Later on, we have fusions of stars, of nuclear fusion to make the light output of stars, and then those stars fuse together in galaxies held together by gravity. All these fusion processes leave relics, leave fossils that archaeological astronomers like me and Steve and others can look into to really investigate what the early universe was like. So I already mentioned the Big Bang, but I want to make a distinction between the Big Bang and a Big Bang. So we have abundant evidence that at least one Big Bang-like process took place. Whether that was what's called a singularity, whether that was a point of infinite density and temperature, we don't have that resolved yet. That's the focus of the research that I do. Versus a corresponding theory that's in opposition to that. That may say there was multiple Big Bangs. In fact, there may be Big Bangs going on all around us in a vast landscape called the multiverse that we'll discuss. So the distinction is, was there a Big Bang? Was there a series of Big Bangs? Was there an infinite number of Big Bangs, even going on to this day? That's the research that we want to go into. And as I said before, it touches on the deepest elements of human nature. The desire to wonder where everything came from. This cartoon here shows, caveman wondering the same question as some astronomer at a telescope. It's basic. We all want to know that. And I like to point out, just think, in a smaller crowd, I'd ask each one of you, what's your favorite day on the calendar? Think about it. Most people say their birthday, their anniversary, Christmas, their baby, kid was born, something like that. Those are all beginnings. Humans are fascinated with beginnings. But the beginning of the universe is not like your own personal beginning. You couldn't witness your beginning, but there were two people there, probably your parents, who can give eyewitness testimony. But nobody can give eyewitness testimony about the origin of our universe. So no one can depict and clarify and actually provide evidence, maybe, that it even took place once versus an infinite number of times. And of course, the first cosmological models date back thousands of years. This is one in the Judeo-Christian tradition. The book of Genesis starts off with essentially a Big Bang-like process. It starts off with the origin of the universe. It's the motto of our college, of our university. Let there be light, fiat lux. That's the motto of the University of California. And it goes into God creating the heavens and the earth. I'm not asking you to believe it or not believe it, but it's very interesting, isn't it? Because the Bible, like the New Testament and the Old Testament, they're mainly books of laws and stories, not like a book about science or the cosmological origin of the universe. And yet, the Bible starts off with this very depiction because it's so central in the quest to understand where do we all come from. Of course, the Hebrews and the ancient peoples were not alone. Here's an Egyptian cosmology, which goes back a little bit less in time, maybe 3,000 years instead of 3,500 years. It depicts an eternal cyclical universe. Instead of a single origin of the universe in the Old Testament, you have a cycle of unending repetition of birth and death of universes. These are central to the old times. Then the Greeks, 4th century BC, Aristotle began to think the universe was eternal, fixed, and centered on the earth. We know now that that's not true. In the Renaissance, people like my other hero besides Barry, Galileo, Copernicus, and others realized that it appears that the earth is the center of the universe, but it's really the sun. And still, it was not known how such a universe could exist. Here's Einstein's hero, the man that made him feel the imposter syndrome, good old Isaac Newton. In his famous and really transformative work called Principia, he talks about a static, steady state, infinite universe. So that is not a universe that has a Big Bang, even though he was quite religious. That's a story for another time. But he did depict it this way. And it influenced his protege 300 years later, good old Albert, so much so that Albert believed the universe was also static, eternal, everlasting. He couldn't reconcile that with certain data that he was availed himself of at the time. So he built into this universe what's called a cosmological constant. We now call it dark energy. Later, he called that a biggest blunder of his life. But even later, his blunder turned out to be probably the greatest discovery of the last 50 years or so in astronomy, the so-called dark energy that's causing the accelerated expansion of the universe. So I always tell people, Steve, as a student, aspire to be the type of scientist that your biggest blunder is actually saying that you made a blunder. And your biggest blunder nets somebody else a Nobel Prize in addition to you. He's a unique individual. A few years after Einstein's conjecture that the universe was static, a Belgian Catholic priest by the name of George Lemaitre, he came up with an idea called the primeval atom that suggested our universe sprang forth like a nuclear process from a point of very, very high density and a volume about the size of our solar system. And from that vast amount of energy compressed in a small space, exploded forth all the rich, luxurious stars, galaxies, planets, people, universities. That all came from this primeval atom. Einstein hated it. He said, your math is good, but your physics is atrocious. This can't be. Because it predicted that there was a day before which there were no yesterday. There was a day in which time itself seemed to spring into existence. It was anathema and it was impalatable. And Einstein hated it until Hubble came along and showed actually Lemaitre's right, Einstein's wrong, and then Einstein had the great humility to admit that he was wrong and say it was a big blunder. Now you all have your tower here. What's the name of the tower that's here on campus? What's it called? The tower. Okay. We have our Geisel Library, which kind of looks like a UFO landed on campus. And I use it to illustrate by the way, it's called the Geisel Library. Many of you are too old to remember or know who Geisel was. He's Dr. Seuss. So Dr. Seuss, so our library is named the Dr. Seuss Library. How embarrassing is that? But it's not as bad, and that's because Geisel retired and lived in La Jolla for the last few years of his life. But it's not as bad as Dartmouth, where he went to undergrad. He donated the money, and now the medical school is named after him. So you can become an MD from Dr. Seuss Medical School. I mean, that's got to be embarrassing, but I digress. What we think now of the timeline, this is another form of what I described before, space-time diagram. As you go back in space, farther out in space, you're going earlier and earlier in time. You come to a time when the first light was formed from the first atoms coming together and fusing into one another. And then later things happen, and more interesting and familiar phenomena, like I say, galaxies, stars, planets, people, etc. But beyond that, you cannot use light to see. You're shrouded in an electromagnetic fog that's impenetrable. So how can you see beyond it to glimpse something farther away and therefore earlier in time, such as the Big Bang moment, if such a thing happened? And the current best accepted model, if you will, for how time and space began expanding is called inflation. It's a theoretical proposition that our experiments are attempting to test, not prove. A lot of people think, they ask me, Professor Keating, what do you want to prove, or what are you hoping to discover? It's very dangerous as a scientist. It leads to what's called confirmation bias, because humans have this ability, remarkably, to find whatever it is they're looking for. And you have to protect against that at all costs. You have to always ask yourself, what mistakes could I have made? And I'm here to admit to a huge mistake that me and my team made a few years ago. And that revolves around this question of what happened at the beginning of our universe, perhaps too, the beginning of time. There are other models. In fact, this is the late, great Jeff Burbidge. I'm honored to have his office at UC San Diego. I should point out that there's an archive, this is unique, and I found it only when I wrote my first book, Losing the Nobel Prize, that are pictures taken by Ansel Adams. And they're stored, guess where they're stored? Here. They're stored at UC Riverside. So I had to get permission. I had to pay my sister campus something like $500 to print this picture of my friend and late colleague, Jeffrey Burbidge. And also his wife, Margaret Burbidge. She had a portrait by Ansel Adams, one of the most famous photographers of all time. There's pictures of her working away. I don't know why she had a microscope, but I think she's looking at spectra of galaxies. And they believed in what was called a steady state universe, but not perfectly static, not unchanging forever, but going through cycles, uncountable cycles throughout infinite amount of time. The universe would expand during part of the cycle, collapse during part of the cycle, but never get down to a singularity, never experience a Big Bang. Jeff, Margaret, their colleagues, they hated this notion of the Big Bang. They felt it was even more distasteful to reason. And many people thought that way, as echoed by Nobel laureate Steven Weinberg. A lot of scientists hate religion. It's sad to say. I think it's actually a shame that scientists and religion are always pitted against each other. I find them to be compatible, but you don't have to believe. You shouldn't believe. I say, I don't even believe in gravity, but I have evidence for gravity. I have evidence for evolution. I have evidence for the early hot, dense state of the universe. That's what we should seek as scientists. It's not a faith-based. There's nothing wrong with faith, but it's not in the realm of science. But Stephen, at least he had the humility and maybe the intellectual honesty to admit that a lot of people hate the Big Bang because it seems like Genesis, the book of the Old Testament. And that, again, is anathema to many atheist scientists. Something like 90% of the National Academy of Science do not believe in the affirmative existence of a higher power. Again, I'm not here to advocate one way or the other. When I set out to write this book, I had to go back to the earliest temple to what I do, which is located in, of all places, New Jersey. Now, I'm a New Yorker, so I can make fun of New Jersey. They always say, joke that we used to say, what do you call the $12 fee to go over the, it's called the Mario Cuomo Bridge or get out of New Jersey? A small price to pay to get out of New Jersey. Now, I don't mean to offend anyone from New Jersey. I love New Jersey. But the origin of our universe can possibly be traced to this very apparatus, which is called the Holmdel Horn Antenna. It's a National Historic Landmark, and it is perhaps a cathedral to science, in my opinion. This horn-like object is pointing down in the picture behind me, but it released data in 1965 with a very humble title. The title was, you can't see it, sorry, but the title was called A Measurement of Excess Antenna Temperature at 4080 Megacycles per Second. Wow, of course, that makes perfect sense. No, it was the first detection of heat, the leftover fossils in the form of microwave photons that would have been produced during the formation of the elements and the expansion until the formation of the atoms. This was the first quantitative fossil ever discovered by cosmological paleontologists. And this set off on a course of discovery that continues to this day, exactly 60 years next year to the day. Since that time, they've built many satellite experiments in space, measured the most exquisite properties of what's called a thermal or blackbody radiation source. And we know without any doubt that in an early epoch in the universe's history, it was far, far hotter, far, far more dense, and the conditions were right for nuclear fusion to take place. Everywhere in space. Imagine this room, but everywhere in this room. A nuclear reactor has a very small reaction chamber. A nuclear bomb, even smaller. But imagine like all of space, infinite amount of space, comparatively speaking. And everywhere in space was suffused with nuclear reactions going on at a rate of 10 trillion per second. And eventually cooling off, that heat associated with fusion eventually cools down and eventually produces the CMB. Now, none of the discoveries that I've mentioned so far prove that the Big Bang happened once or was what's called a singularity, a point of infinite temperature, infinite density. It only suggests that if we go back in time from today on Wednesday and go back 13.8 billion years, you come to some Wednesday, and then you know for sure there was no Tuesday perhaps, but you're on this day, you're on this Wednesday, and you can keep going back a little bit further, and that's the limit of what we can investigate using tools of modern physics, particle accelerators, nuclear reactors, etc. And beyond that, you must speculate until now. Until now, when we built telescopes that can see the fusion products left over from the formation of space and time itself. These are called gravitational waves, very similar to what Professor Barish won a Nobel Prize for with the LIGO experiment, except those gravitational waves were from two black holes that collided together, fusing together, and emitting gravitational radiation as excess energy. Imagine all the matter, all the black holes in the entire universe effectively springing into existence at one moment in time. Far, far more gravitational waves were produced at that epoch, if it took place. So we don't know if this took place, and there are many alternative hypotheses, including by some fellow Nobel Prize winners like Roger Penrose, who also believes in a cyclical type of universe. This is not unique, it's not new, it's been going on for literally thousands of years. This is not what we call settled science. And so it's very, very fertile ground for young people like you, perhaps, to investigate, to get involved with, because that means there's many, many things we don't understand. When you don't understand something in science, surprise is the greatest emotion that you can feel. So some people believe the universe came from a pre-existing universe that crunched down, ignited another universe from its collapse. Some say it didn't collapse to a singularity, it merely got down to a finite distance scale, so it's not a quantum mechanical singularity for those aficionados out there, and instead cycles through space and time unending number of times. This is, again, not the same as a single Big Bang. Very different models. Infinite number of cycles, infinite quantum mechanical singularities, infinite classical singularities or non-singularities, etc. And then there's the third option, which is the one that we're most focused on in the field today. It's called eternal inflation, which effectively means that somewhere in a vast cosmic landscape, In every point in space and time, there are universes being created. Some are getting destroyed. Some have properties just like our universe. Some are very different. In one universe, you're up here speaking, I'm in the audience. Literally, an infinite number of universes. Infinity is a pretty big number, especially as you get close to the top. So anything can happen in the so-called multiverse theory, which underpins the inflationary universe, which predicts that waves of gravity come from the singular origin of the universe. And here are the two founding fathers of inflation, Alan Guth and Andre Linde up at Stanford. And they both agree, cannot have inflation without the multiverse. And these stakes are very high, right? Do you exist? Does your God exist in another universe? Philosophically, it's a very, very fraught and perilous, but also fascinating question. There are many types of multiverses. As a fact, there's 4 different types of multiverse. Don't get into those differences in the multiverses. That's not a talk for a different time. But I just want to highlight what a good scientist should do. This is a table that I made, influenced by a very, very famous philosopher of science named Karl Popper. Popper said the following. He said, scientific theories can never be proven. In other words, I can't prove to you that right now on Neptune's North Pole, there's not a purple unicorn. That would make my daughters really happy, but I don't think it's happening. But I can't prove that that unicorn is or is not there. You can't prove something in science, period, full stop. You can exclude everything else. Exclude means falsify, disprove theories. That's what we're very good at doing. So science is the occupation of disproof, not proof. That's why I don't like it when people say, what are you hoping to prove with your experiment? It leads you prone to confirmation bias, and it also misleads people into what science is all about. So Popper is saying you should do an experiment, and that experiment should be able to prove something right or wrong. In fact, he hated astrology. And he came up with this rubric for grading scientific theories or non-scientific theories based in part upon both the so-called science of astrology and the so-called science of dream interpretation and like phrenology, reading bumps on people's heads. He said those things were so flexible you could accommodate anything. And so if you predict, you said you're a Virgo, but you're really a Gemini, the same thing happens. That is not falsifiable. I cannot prove that astrologer wrong that I mentioned in the beginning of the talk. Therefore, astrology is not science. Look for things that cannot, not that they can be proven right. Look for that which can be possibly proven wrong or falsified. And you'll converge on scientific truth. Here's a scorecard of the different things, the different models I've talked about, the steady state model, a bouncing model, an inflationary multiverse, and a cyclical universe as well. And all of these, except for the inflation, can be disproven, falsified. So it's an interesting state to be in. We may never be able to effectively falsify or prove inflation, but we can get very, very close, a close approximation to the truth. And sometimes that's all you can do as a scientist. Scientists are expected to always have the answers, but really it's about having the right questions. One thing I learned from Barry is that in this book, I talk about it in the interview with him, he says curiosity is the most important human emotion. Curiosity impels you to discover new things, to be open to new surprises, to be thrilled when you discover something new. But we kind of beat it out of kids. Like anyone who's a parent knows, the kid keeps asking you why. The eventual answer that will suffice is because I said so. But that's not good. You're kind of beating the curiosity. Curiosity killed the cat. You've heard that, right? Those are negative associations and connotations of curiosity. It should be the opposite. It's the most cherished of all emotions for scientists. So we want to build a decisive experiment that could disprove alternatives and leaving behind the most close shred of approximation to truth. We use a tool called cosmic microwave backgrounds polarization. I'm not going to get into the great details of it. I'll show you an image on the right that shows what the universe would look like if inflation took place and there was a quantum mechanical singularity at the origin of our current universe. You'd see a pattern of the polarization state of light. And in fact, this drove me in 2000 to start thinking about a way to build an experiment to look for the signal to disprove 3 different models of cosmology. And then what would be left might be the closest approximation to truth. So here's the logic. This is all we need. this is the end of technical kind of details. If the universe began with an inflationary Big Bang, it will have produced gravitational waves astronomically larger than the ones detected by LIGO, but so far away in both space and time that their signal on Earth is minuscule. So we can't use detector like LIGO to detect gravitational waves from inflation. We can use a detector that's closer to the source of the explosion, if you will, and that's the CMB itself. We use the light from the first atoms. We use those as our detectors. Our detectors are 380,000 years. We move them back. That's where they are. They're at the surface that the CMB shows us. And then we can measure them today from various locations around the world. And in 2000, as I said, I proposed the first experiment to really do this job of measuring this with my colleagues at Caltech, Jamie Bach and Andrew Lang. And this was to build an experiment called BICEP. We later upgraded to BICEP 2. It's the simplest type of telescope you can imagine. It's a refracting telescope. It's tiny. It's about 8 or 9 inches in diameter, the lenses of it. It's just like Galileo used in 1609, 1610 to give evidence for the Copernican model of the heliocentric universe. It has 256 detectors at this time, at the time in which we deployed it and made measurements. It's only about 10 feet tall. And instead of being able to keep it here in Southern California, we had to take it down to the bottom of the Earth. So now we're going to go on a trip. We're going to cool off from these warm Santa Ana conditions by journeying down to the South Pole, Antarctica. The South Pole is the southern axis on which the Earth is rotating. All time zones, all lines of longitude converge at the South Pole. Technically, there's no north, south, east, or west. Everything is north, moving away from the South Pole. I've been there twice, and I'll take a quick history lesson. It was only discovered, imagine 1/7 of the continents on Earth were not really explored until 112 years ago, next month. This picture, this selfie, was taken by a team of British scientists and explorers led by Robert Falcon Scott. And the reason that he's saying this is an awful place, he skied 700 nautical miles from sea level up 9,000 feet, higher than Big Bear, on ice over 2 or 3 months almost. And he got to the very closest approach to the South Pole, and he started to see something on the horizon. And he said, oh, bleep. Because if you notice, that's not a British flag, that's actually a Norwegian flag. He had been beaten by 3 weeks. This was like landing on Mars. Be like landing on the moon and Neil Armstrong steps on a Soviet Union flag. It was the most depressing experience probably in history. It was the end of all exploration of the unknown parts of the world. And he lost it by 3 weeks. So they all died. All these guys died. They didn't get close enough to their food supplies that they had left caches for, and they ended up dying about a couple of weeks, maybe a week and a half away from being saved. And it's still a very treacherous and dangerous place, as this video that I took displayed. The inhabitants are cruel. They're like those UCLA Bruins. Boo, Bruin. No. Okay, so those are some penguins. They get along like my sons do. But maybe it's just penguins that they don't like. You know, maybe they have sibling rivalry. No, they don't like people either. And they're actually vicious beasts, these penguins. Don't think they're all cuddly. So you get to the South Pole, you're negative 90 degrees latitude. You get to the South Pole, you take your selfie, you post it on Instagram. And this is where the explorers reached 112 years ago. We put our experiment in this building on the left, which is this blue building called the Dark Sector Lab. That's the outhouse. There's no indoor plumbing at the South Pole. You go out there in freezing conditions, winter or summer. By the way, the sun is up 6 months of the year and it's down 6 months of the year. It's pitch black. You cannot see a few feet in front of your face. And scientists live there and they compete to be the person that gets paid to go there. It's incredible. So remember that swirly pattern that I said was the kind of indicative evidence that inflation took place? And if we discovered it, we'd be discovering inflation. And by the way, if inflation takes place, there's a multiverse. So there's an infinite number of you. and maybe some religions are right and some are wrong. The stakes are incredibly high. We announced 10 years ago that we discovered it. We discovered this twisting, swirling pattern of microwaves that indicates gravitational waves, that indicates inflation, that indicates the multiverse. We were the toast of the town. This is our actual map. It was printed in newspapers. It was on the front page of the New York Times. It was on the front page of the most important newspaper in the world, the San Diego Union Tribune. Come on, I know we all subscribe to that here. And it was also in The Economist. I love this headline in The Economist, which is a stately British magazine, because it sounds like just like some dude is watching, so is this the beginning of the universe? But that's what we claim to have seen. We were claiming that we saw the spark that ignited the Big Bang expansion. So it was rightfully so. It was on television, CNN. We had a big press conference. But always in the back of your mind, you always have to think of not the ways of glory that you're about to receive, but how you may have sinned, how you may have done mistaken conclusions, how you may have fallen victim to confirmation bias. In our case, what brought us down to earth, literally, was the smallest substance in the world, in the universe. It's called dust. In this case, cosmic dust. And it's nothing more than these little meteorites that I'm going to give to those of you who pick up a copy of my book, and I'll give to everybody who eventually joins my mailing list. These are microscopic meteorites that exist in our galaxy and get aligned by the Milky Way's magnetic field. And they can exactly mimic the swirling, twisting pattern of microwave. And that's exactly what happened. 6 months later, we were humiliated to learn that what we saw was dust, not gravitational waves, not inflation, not the multiverse, not the Big Bang. We saw schmutz, space schmutz, effectively. It was humiliating, especially since we had been told that we would win the Nobel Prize. We guarantee is all we need to do is get confirmed. Well, we never got confirmed. And in fact, the hunt is still on for this very signal. This is the process that talks about this. I explain it more in my first book. So instead of seeing the universe like this, clean, pristine, beautiful, as the word cosmos means, peering back to the beginning of time, perhaps. No, it's exactly like Westwood, Los Angeles. It's a horrible, no, I love LA. I know you guys are, some of you from LA. It's a smoggy, filthy, dirty place. It makes my kids seem clean. The universe is rotten with pollution from the explosion of stars, which, by the way, is a good thing because none of us would be here if that didn't take place. For the iron molecule inside of the hemoglobin that is in our blood has the exact same chemical composition as the meteorites that I'm going to send you. The iron comes from the death of stars. As Carl Sagan said, we are star stuff. And it's quite poetic, but it also can take away things like Nobel Prizes. So here's a picture of the Simons Observatory collaboration, which rose from the dust like a phoenix rising from Arizona. Like a phoenix rising from the ashes of this BICEP 2 experiment. Here's our collaboration. Big role is played by Professor Choi, Steve Choi's group here, UC San Diego. We're located in Chile, 375 researchers, all 7 continents. It's quite a large collaboration, and it's all thanks to the visionary generosity of the late, great Jim Simons, who passed away this past May. And he was like a father figure to me. I talk about him a lot in my first book. So it's a big team, but we needed to go after the goals that I'm going to describe for you. We even have an animated logo. Those things don't come cheap. So what is the Simons? Well, it's a super sucker that sucks up dust in the cosmos. No, it doesn't do that at all. The Simons Observatory is a telescope that is built not only to see the waves of gravity from the cool Big Bang inflation, it's built to see dust. Yes, you heard that right. We built our experiment focused in large part to see dust so that we can remove it like a vacuum cleaner, not exactly, but effectively remove it from the data. So we take in the data from this location in the Atacama Desert in northern Chile. It takes about 26 hours to get there. We turn this bare site that looks like this. This was it in 2019 when we broke ground on the telescope. It's located here. This was all rocks, like the surface of Mars. We had to fully instrument this site, and now this is what it looks like. This has taken over $100 million to get here. even before we took our first data point, which we started getting in April. And thankfully, Jim Simons was able to see our very first light data a month before he passed away on his birthday. Here's a picture by hometown hero, Michael Randall, who will be Dr. Michael Randall in a few months at my lab. He graduated from here in 2018, and he spent a lot of his graduate life there. So if you want to follow in his footsteps, I'm always looking for brilliant young mountaineers. So please do avail yourself, be in touch with me about that. There's Michael helping to install this enormous 6-meter diameter telescope called the Large Aperture Telescope. Here's him with the small aperture telescope. This is just how we built the telescope, constructed it. There's Michael in the lab. These telescopes are quite small. They're also refracting telescopes, using lenses only, and they work on very similar principles, except they, unlike BICEP, have the capability to measure dust and the cosmic microwave background radiation at the same time. These things use detectors cooled down to 0.1 Kelvin, 100 millikelvin above absolute zero. It's a really extreme technology, and we're at very, very inhospitable conditions. There's Michael, all these pictures are of him. You see the size of the telescope. That one we called cosmic plasma. This one was built at UCSD. We called it B-Rock. I don't know why. CMB, Beastie Boys. And then on the left, you see what we have to wear when we're up there. We have to wear sturdy boots, sunglasses, protective gear, helmets, and then most importantly, we have oxygen. The atmospheric pressure is half of what we feel right here in Riverside. It's a very, very alien environment. And for that reason, they do test Mars rovers and astronauts do train there. Technology was built by one of Steve's co-thesis advisors, Suzanne Stagg. She built the detectors, designed, built the detectors, tested them. Cornell, when Steve was a graduate postdoc up there. So again, what are we trying to do? We're not trying to prove inflation took place. If anything, we're trying to see if inflation took place. Very different philosophical proposition. What we're trying to do is disprove the alternatives, that the universe is eternal and static, that the universe goes through infinite number of cycles, that the universe had a bounce associated with it, or endures forever until it's swallowed up into a black hole. That's the CCC model, effectively. All three of those can be disproven if we see the twisting pattern of microwave polarization. It disproves and therefore falsifies those other models because they explicitly forbid that pattern to appear. So you understand, we're trying to prove those three models wrong, and then the last survivor, maybe, provisionally, it may be right. We'll have to probe and study it in even more detail. So again, inflation comes alongside, part and parcel, hand in hand with the multiverse. And I didn't talk about what I sometimes call the mastodon elephant in the room, and that's this question of God. And the multiverse, by some people, is considered bad for science. And if something is bad for science, it's bad for you. It's bad for society. So the stakes in what we're doing with cosmology, you wouldn't think of it. You think of it as, oh, guys and gals are looking through telescopes. What's the big deal? No. Some of this has implications on the very foundations of called epistemology, which is the search for knowledge and the tools at which we acquire knowledge. Some have impact on philosophy and even theology, as explained here, because a multiverse really says you have an infinity of universes. Therefore, anything that can happen will happen. All of you are in some universe giving a talk up here. I'm in the audience, and others, you're a righty. Well, you're a lefty in that universe. Some universes last a quarter of a trillionth of a second. Some last for 10 trillion years, longer than our universe. And because there's so many of them, anything that can happen will happen somewhere, somehow in the multiverse. So a lot of people feel this is anathema to the way good science should be done. It's too flexible. It can't be falsified. And those are strict adherents to Popper's ideas. I'm not saying they're right or wrong. But eventually it devolves. And it's as unfalsifiable, unprovable as the proposition that an unseen creator created the universe right now, implanted in our minds memories that we were lining up for fruit and cheese an hour ago. It could happen. It's not philosophically, it's not forbidden, therefore it could happen. So Professor Paul Davies, Arizona State, has this great quote that the multiverse theory may be dressed up in scientific language, particles, fields, forces, but it requires a leap of faith, just like religion. Remember, faith, trust, etc., belief, those aren't part of science. It's not saying that they're bad, but it's not part of science. We look for evidence, and that's what distinguishes us. Okay, I want to close with this picture taken by my friend. Shout out to Brent. His real middle name is Danger. That's pretty cool. You find him on Instagram there. Plug, shout out to him. He took this picture in Arizona, and it depicts, to me, what we're doing in this field. It depicts the vast cosmos beyond. It depicts this structure made of a giant ball of dust called the Earth. The Milky Way is polluted with dust, as I said. And then you see these two figures. Can't see their faces, don't know who they are. But in their blood courses the same iron that was produced in the same supernovas, that produced the same dust, that produced the Earth, and the same dust that swept away my Nobel Prize. I'm not bitter. I'm not bitter. But it's really cool that this image really brings together these three different ways that dust is essential. It's also a nuisance. And that's what makes being a scientist so magical. So I want to end here and remind you, you can get a copy if you're the first 20 people. Sorry, I didn't bring too many. Again, so blessed to have so many of you come out tonight on a Wednesday night in the middle of November. But I hope you learn from this book that I wrote as a self-help guide for young scientists like you. Thank you very much. I think we're going to take questions. All right. What's that? Yeah, everyone's leaving.
Thanks for the talk. I've been essentially.
Oh, I appreciate that. Thank you. Yeah, it's really fun to speak to this big. Thank you, Dean. Thank you so much. It's great to be here. Thank you. I think they want us outside. Oh, I'm fine with it here. Yeah. Want to? Yeah, yeah. Okay. You're not alone.
You know, so let's say you guys,